Good morning, everyone. So last time we looked at the electric and the magnetic field, and we showed that in the special relativity, E field and the B field actually can combine together and form a rank 2 tensor. And more precisely, this is an anti-symmetric rank 2 tensor, where the diagonal term is 0 and the off-diagonal term takes opposite sign for the opposite elements. Okay. And we showed that because this is a rank 2 tensor under Lorentz boost, it must behave like this. If we transfer from one reference frame to the other reference frame, in the new reference frame, the value of E and B field and the value of E and B field in the old reference frame must be connected by this rank 2 tensor transformation, with one Lorentz boost multiplied on one side, another Lorentz transpose Lorentz boost multiplied on the other side. Okay. And this immediately tells us how E and B field transform from one reference frame to another reference frame. Today, we will continue our discussion about E and B field. Okay. So the first topic we're going to look at is the Maxwell's equation. We'll look at Maxwell's equation again. So in the previous lecture, in the lecture last week, we showed that if we can rewrite Maxwell's equation in terms of scalar and vector potential phi and A. Okay. And we showed that if we use phi and A forms a vector, and the Maxwell equation for phi and A indeed satisfy the structure we mentioned earlier on. It has vectors on one side equals vectors on the other side. One side is the derivative of phi and A, which is a vector. The other side is a 4D vector of charge density and current density, vector equals vector. So today we will go back to the original form of Maxwell's equation in terms of E and B, and show that this structure also obeys the scalar equals scalar, vector equals vector, tensor equals tensor structure. Okay, and this is actually expected because we know that A field satisfies this structure. The Maxwell's equation for A and phi field satisfies this structure. And we also showed the last lecture, the relation between E and B field and A field satisfies this scalar equals scalar, vector equals vector, tensor equals tensor structure. Thus, if we go back to the E and the B field Maxwell's equation, it must also satisfy this relation. Okay, so here we will not go into too much details, just briefly gives you the conclusion. Okay, so the Maxwell's equation, it turns out we know we have four of them, four sets of Maxwell's equations. Let's first look at the first one and the last one. Okay, so this first Maxwell equation and the last Maxwell equation, they have something in common. They have charge density and current density. Okay, they care about the motion of charge particle. The other two equations do not have rho and J built in. Okay, so let's first look at the two equations with rho and J built in. Okay. These two equations can be combined together in a tensor form like this. Okay, so on the left-hand side, we have E and B field. We know E and B field are part of a rank 2 tensor, and in the last lecture, we labeled that rank 2 tensor as F. Okay, by the way, this rank 2 tensor, we gave it a name, which is F, which is electromagnetic tensor F. So F is the tensor form of E and B. Okay. So on the right-hand side, we have derivative of F, and on the left-hand side, we have derivative of F, which means derivative of E and B. On the right-hand side, we have some physics constant, mu0, epsilon 0, and the charge density and the charge current. We know that charge density and the charge current also form a 4D vector, which is our 4D current density vector. Okay, and we called it J, as we defined earlier. Okay, so one side we have derivative of rank 2 tensor, the other side we have vector. Okay, so derivative of rank 2 tensor and the vector, how can they equal to each other? Well, the only thing we can do here, the one thing we must do here is to make the left-hand side also a vector. Because the right-hand side is a vector, left-hand side must also be a vector. So how do we make the product of a vector, derivative is a vector, and the tensor to be a vector? Well, actually the answer is simple. We just need to do a inner product. Okay, we know that the inner product between a vector and a vector gives me a scalar. Okay, so inner product always reduce the number of sub-indices. Okay, and if we have vector, we have four indices, multiply the inner product, we have only a scalar with one sub-index, or with no sub-index, if you like. Okay, so here, if we do a inner product between the partial derivative and f nu nu, the rank 2 tensor, and make sure that the inner product, the inner product require the derivative, the subindex of the derivative and one of the index of the mu to be the same. And when we sum over mu, the only index left over is nu. So we have a 4D vector. So this is the inner product between a vector and a tensor, which gives me a 4D vector. And this 4D vector equals to the 4D vector. Okay, so that means the first and the last equation of Maxwell satisfies the vector equals vector structure we mentioned earlier. And the other two equations of Maxwell, this one and this one, the middle two, this two is a little bit different. Okay, this two, first of all, let's move this B field to the other side of the equation. Okay, if we move B field to the other side of the equation, both this equation has some derivative of E and B equals 0. Okay, and the derivative of E and B, derivative we know is a rank 4 vector, and the E and B field is a rank 2 tensor. Okay, so for the other two equations, it turns out that is also a product between derivative vector and F tensor. Okay, but that product is not the inner product. It's the exterior product we defined earlier. We defined in the last lecture. Okay, so in the last lecture we defined the exterior product between two 4D vectors. It turns out this exterior product can be generalized to vectors and the tensors, tensor and the tensors, etc. Okay, and here this product between derivative and f mu mu is actually the exterior's product. And if you do exterior product between a vector and the tensor, rank 2 tensor, this guy is actually a rank 3 tensor. This whole thing is rank 3 tensor. Okay. The other side of the equation, we typically write it as a 0, but it's actually not a 0. It's a matrix of 0. It's a rank 3 tensor of 0. It's a rank 3 tensor. This 0 means it's a rank 3 tensor. Every single element of that rank 3 tensor is 0. Okay. So this equation is also obeys the rank 3 tensor equals to rank 3 tensor structure we mentioned earlier. Okay. So the bottom line, the Maxwell field, the Maxwell's equation, if we written in terms of E and B, this equation still obey the scalar equals scalar, vector equals vector, tensor equals tensor structure. Okay. It turns out that the first set and the last set of the equation, the Maxwell's equation, gives us this. It follows the vector equals vector structure. One side is the inner product between derivative and f mu mu, which is a vector. The other side is a charge density vector. Charge density and the current density vector, which is also vector equals vector. The other two sets of Maxwell's equation combined together in this form. This is the rank 3 tensor equals rank 3 tensor equation. And on the left-hand side, this rank 3 tensor is from a vector multiplied to a rank 2 tensor, but this multiplication is the exterior product. So exterior product of vector and the rank 2 tensor give us a rank 3 tensor. Exterior product increase the subindices number and increase the rank of the tensors. Okay, so that's the E and the B field and Maxwell's equations. There's one more topic we want to discuss about the E and B field. That is, we know that E and B field are part of rank 2 tensors, but it turns out we can use E and B field to build some scalars. And these scalars are very useful for various things. And we will see some examples in your homework this week. And we will also revisit this topic in the next chapter when we discuss about the Lagrangian and action formalism of E and M of electromagnetic dynamics. Okay, so this is something that will become very useful in the later part of the semester. But here we'll just briefly touch this topic and gives you a hint, which we will use later. Okay, so E and B field. The focus of this section is we want to use E and B field to build two scalars. Okay, so actually in your homework, you will check this. We will show that this object, E squared minus B squared, with coefficient C squared, okay, and E dot B. Okay, so these two objects, obviously they are 3D scalars. Okay, so the E squared is the absolute value of E, length of E. B is square is the length of B. Under spatial rotation, E and B both the direction can change, but the amplitude will not change. So this is a 3D scalar. E dot B is also a 3D scalar. The dot product between two vectors, two 3D vectors, is scalar. So these two quantities obviously are 3D vectors, but are they 4D vectors? Sorry, these two quantities are obviously 3D scalars. Sorry, what I mean is scalars. Okay, so they are obviously 3D scalars, but are they 4D scalars? Okay, so to check whether they are 4D scalars, what we need to do is we need to do a Lorentz boost. If these two quantities are 4D scalars, then under a Lorentz boost, they should remain exactly the same. They should not change. Okay, so in the new reference frame and in the older reference frame, this quantity should remain the same. The value should remain. Okay, and that's the way to prove and to test or to verify, to prove whether these quantities are 4D scalars or not. And that will be a job for you in this work's homework. So in this work's homework, you are going to show that this quantity and this quantity stay the same under Lorentz boost. Okay, we know how E and B transforms under Lorentz boost here. Okay, we'll use a Lorentz boost formalism for E and B to check these two quantities as scalars. They don't change under Lorentz boost. Okay, so this conclusion is very useful and very important, and we will utilize that later in the next chapter. And you also utilize this conclusion in this week's homework to prove a couple conclusions. Okay, and this is actually a very powerful conclusion. It can help us in a lot of situations. Okay, so let's come back to today's lecture. So in today's lecture, instead of prove these two objects as 4D scalars, I will just demonstrate to you how this cartoon picture, or I will demonstrate how do people think about these two constructions? Where do this scalar structure, where does this scalar come from? Okay, so in your homework, you will prove that they are indeed, you will give rigorous proof to show that they are indeed scalars. But in this lecture, we'll look at where does this scalars come from. Okay, so first of all, we know that E and B field forms a rank 2 tensor. That's what we call the F tensor. Okay, as we defined earlier. So E and B field, we call this tensor F tensor. Okay. So if we have a tensor F, or any tensor, and we want to make a scalar out of this tensor, there is one simple way to do that. Okay, no matter what tensor, what rank 2 tensor we have, we can multiply that rank 2 tensor with a metric tensor. Okay, and then we take a trace. Remember, rank 2 tensor is a matrix. Metric tensor is also a matrix. Matrix times matrix is stereo matrix. Okay, so this is just a metric product. For a metric product, then we can take a trace, adding the diagonal term together. Okay, this object turns out is always a scalar, no matter what rank 2 tensor you use. Okay, so to prove that it's not complicated, okay, so first let's do a Lorentz boost or any 4D rotation. And the Lorentz boost or any 4D rotation, we know G becomes G prime, F becomes F prime. And because F is a tensor, F under Lorentz boost becomes this. Okay, it has one rotational matrix or Lorentz boost matrix on one side and the transpose on the other. Okay, G, we know G, the metric tensor, stay invariant under Lorentz boost, right? And if the metric tensor stay invariant under Lorentz boost, it is their G. Okay, and then we utilize an important trick of trace. Okay, for trace of a bunch of matrices multiplied together, we can switch the orders. We can move the last matrix to the front and then calculate the trace, and the value will remain the same. So trace matrix A times B equals trace B times A. Okay, so for two matrices A times B and B times A, we know for matrices A times B and B times A usually are not equal to each other because we cannot switch the order for matrix product, but their trace will stay the same. Okay, so I can switch the order, move this RT to front. This matrix will be a different matrix, but the trace will always stay. That's a property of a trace. Okay. Then we utilize a property where rotation, 4D rotations don't change the metric tensor. 4D rotation don't change the metric tensor means RT times G times R is their G, is their the metric tensor. Okay. So at the end of the day, we find that the trace of F and G times F after the Lorentz boost, after the rotation, is the same as trace of G and F before the Lorentz boost. Okay. So this using metric tensor and using trace is one very standard and one very efficient way to get scalars out of tensors, etc. Okay. Okay, so this is a very obvious way to get a scalar. But for E and B field, we can't use this to get a scalar. Okay. The reason for that is for E and B field, if we do our F is, by the way, again, F is our E and B field tensor. Okay. If we calculate the metric tensor times F and the trace, this guy is doomed to be 0. Okay, this guy is always 0. And the reason it is 0 is because f is an antisymmetric tensor, as we mentioned earlier. For antisymmetric tensor, when we take the trace, everything just cancels out, the trace is 0. Okay. So this indeed is a scalar. 0 is also a scalar, right? But this scalar is a trivial scalar. It's not useful. It does not contain any information about the E and the B anymore. It's just 0. Okay. So this simplest way to construct the scalar doesn't work. So we need to do something a little bit more sophisticated. And the next way, the next one, the next order of this structure is GF. Okay, metric tensor times F tensor, times another metric tensor times another F tensor. This one we can show using the same technique. This one is also a scalar. Okay, for example, this GF trace under Lorentz boost becomes G prime F prime G prime F prime. Okay, again G doesn't change under Lorentz boost. G still remains the same, and F changes as R on one side, R transpose on the other side. R multiply on one side, R transpose multiply on the other side. That's the Lorentz boost of F. Okay, and then again we reorder this matrices. We move the last R transpose to the front. We move the last R transpose to the front, and again because we are doing the trace, moving this R transpose from the last one to the front, then change the trace. Okay. And then here we utilize the fact that RTGR is the same as G. Okay, we group RTGR together. We group this RTGR together. This RTGR is a rotation, Lorentz boost of metric tensor. And we know Lorentz boost does not change metric tensor. So this RTGR is G, RTGR is G. So we go back to the same formula, in the K frame. So in the K prime frame and in the K frame, this trace remains equal, remains the same. Okay. So this, by the way, this construction of scalars can be generalized. You can multiply more G and F together. You can do GF trace. That's a scalar. GF trace. That's also a scalar. So this is very generic. It's basically GF to the nth power. Take a trace. You will get a scalar. Okay. If the power is 1, here we get 0. If the power is 2, what do we get? Well, we get E squared minus B squared. Okay, so if we calculate this trace, where F is what we defined in the previous lecture, it's the E and B field. Just multiply this matrix together and calculate the trace. This is exactly E squared minus B squared. And this is one way to prove E squared minus B squared is a scalar. Okay, so in your homework, you are not use this way to prove it. You are do directly the Lorentz boost to show it is a scalar. It stays invariant. And the origin of this scalar comes from this construction. Okay, this is how we get a rank 2 tensor, go back and turn into a scalar. Okay, so that's one of the scalar. So what about the other scalar? Well, the other scalar obviously is not through this construction. Okay, this construction will not give you E dot B. Okay. So the other construction, the other scalar actually comes from a different construction. Okay, so it's a different way to multiply E and B field together. That multiplication there turns out what we need is the so-called there is the exterior product we defined early on. Okay, so we defined in the previous lecture the exterior product between two vectors. Okay, and as I mentioned earlier today, exterior product can be generalized to actually vectors and tensors, etc. Okay, so here what one need is the exterior product of F to itself. Okay, so I have F tensor. This is my E and B field rank 2 tensor, multiplied to the F tensor, E and B field tensor again, but this multiplication is the exterior product. Okay, and this exterior product, I don't want to go into too much about the mathematical details. If you are interested, you can drop by in the office hour and we can talk about the details. But basically, the bottom line is the exterior tensor between F and F. If you calculate that, it gives you a very simple structure. It is E dot B, a scalar, times rank 4 tensor. Okay, and this rank 4 tensor epsilon mu beta lambda gamma. This rank 4 tensor is a 4-dimensional Levi-Civita symbol. Okay, so this is we are very familiar with 3D Levi-Civita symbol, which we use for cross product, etc. Okay, so the 4D version of Levi-Civita symbol is very similar to 3D. Okay. First of all, this object, every single element of this tensor is either plus, minus 1, or 0. Okay? If any two elements are equal, then it's 0. Okay? If all the four elements are different from each other, then any four indices of this mu, beta, lambda, gamma are different from each other. Then the element is either plus 1 or minus 1. Okay? And how do we know it's plus 1 or minus 1? Well, we define epsilon 0, 1, 2, 3, 4. Sorry, 0, 1, 2, 3. If mu is 0, beta is 1, and the next one is 2, and last one is 3, we define that one to be plus 1. Okay? Then for any other order, if we switched even times, it's plus 1. If we switch odd times, it's minus 1. That's exactly the same as 3D Levi-Civita symbol. Okay? So this is a 4-dimensional antisymmetric rank 4 tensor, a 4-dimensional version of Levi-Civita symbol. Okay? And because the exterior product is a rank 4 tensor, this epsilon is also a rank 4 tensor. And this equation, we must obey the rank 4 tensor equals rank 4 tensor structure. So E dot B, we have no option. It must be a scalar. A scalar times a rank 4 tensor is a rank 4 tensor. That's the only way to make sure that we have rank 4 tensor equals rank 4 tensor. This is another way to get a rank 4, another way to get a scalar out of E and B. And that's the second scalar, E dot B, we have here. Okay. It turns out we can prove this, but we will not spend the time to prove this. I'll just give you the conclusion. If we want a quadratic form of E and B, quadratic form means either E squared, B squared, or E times B. Okay, it's quadratic order. If we want the quadratic form of E and B to be a scalar, these are the only two. Okay, this is one. This other two, other one. These are the only two. There's no way to get any other scalar from E and B, their quadratic form. Okay. Okay. So these are the two scalars, and we demonstrated where do they come from. And there is one more thing I want to mention about this E dot B scalar. Okay. That is this formula, exterior product of F gives you E dot B. We can rewrite this formula in a slightly different way. Okay. We can rewrite the same thing, E dot B, like this. Okay. So it's F rank 2 tensor, F rank 2 tensor multiplied with the Levi-Civita symbol, the 4D Levi-Civita symbol, epsilon. Okay. This whole thing is a scalar, and that scalar turns out to be E dot B up to some constant, physics constant coefficient. Okay. The reason I want to mention this formula, this is also E dot B, is because this formula is actually a 4D generalization of 3D mixed product. Okay, if we think about 3D mixed product between A, B, C, 3 vectors, and write down its components, it looks very much the same as what we have here. Okay, in 3D, the Levi-Civita symbol has 3 index, ijk. Okay, so we need 3 index to match it. That's why we need 3 vectors. That's why 3 vectors can define a mixed product and get a scalar in 3D. In 4D, the Levi-Civita symbol has 4 indices. So we need 4 indices to match this Levi-Civita symbol to define a mixed product. Okay, and in order to get 4 indices, we need 2 rank 2 tensor. Each rank 2 tensor gives me 2 indices. 2 of them gives me 4. That gives me a perfect match. So this is a 4D version of mixed product. Okay, same as in 3D. 3D mixed product gives me a scalar. 4D mixed product also gives me a scalar. That's the E dot B scalar. That's another way to understand E dot B as a scalar. Okay. And this analogy between 3D mixed product and 4D mixed product gives us actually one more important lesson, one more important conclusion. That is, this scalar we get here is not a regular scalar. It's a so-called pseudo scalar. Okay. So in 3D, we know that if we have 3 vectors, these are the 3 regular vectors, not pseudo vectors. Okay. We have 3 regular vectors, and we do a mixed product. Indeed, we get a scalar, but that scalar is a 3D pseudo scalar. 3D pseudo scalar means under spacing version, it changes sign. Okay. A regular 3D scalar does not change sign under spacing version, but the pseudo scalar changes sign. Okay. So scalar and the pseudo scalar under rotations, they behave the same way. They don't change under rotation. But the difference is under space inversion. Regular scalars stay the same. Okay, like electron mass, rest mass of particle, etc. Those things actually stay the same. But the pseudoscalar, if we do a space invariant, it changes sign. Okay, so this E dot B term is a 4D variant of mixed product. Okay, so this 4D variant mixed product has the same property as 3D. This 4D mixed product gives us scalar, but this scalar is a 4D pseudoscalar, not a 4D regular scalar. Okay, it's a 4D pseudoscalar in the sense if we do a space invariant, or if we do a time reversal transformation, if we flip the direction of time, then this object will change sign. Okay, either we do under time invariant, it changes sign. Under space invariant, it also changes sign. That's called a 4D pseudoscalar. Okay, so this is a 4D pseudoscalar, where E square minus B square is a 4D regular scalar, is a 4D scalar. E square and B minus B square does not change sign under space invariant or under time reversal transformation. Okay, E dot B is a pseudoscalar. It changes sign under space invariant or time reversal transformation. Okay, so to realize that, to verify that, we can look at the what we can use what we learned in E and M1. In E and M1, we learned that under space invariant, so if we flip the direction of space, E changes sign, but B doesn't. Okay. If E changes sign, but B doesn't, then for E square and B square, the whole thing doesn't change sign. Okay. B changes sign, but square it, the sign remains. But for E dot B, it's different. For E dot B, under space invariant, E changes sign, so we get minus sign. B don't. And the result, E dot B will change sign under space invariant. Okay. So for time reversal, it's the same story as we learned in E and M1. Under time reversal, E stays the same sign, but B flips sign. Okay. If E stays the same sign, B flips sign, then when we square it, everything remains the same. So it's a regular scalar. Okay. But for E dot B, under time reversal, E remains, B flips sign. Okay. So the whole thing flips sign. E dot B changes sign under time reversal, and E dot B changes sign under space invariant, whereas the others doesn't. Okay. And the fundamental reason is because this E dot B scalar comes from a 4D variant of mixed product. So it changes sign. This is the pseudoscalar. Okay. So this is actually this is actually a very important difference between these two scalars, and we will come back to this difference in the next chapter when we discuss about the action and the Lagrangian formalism for E and B field. Okay, so one more thing I want to briefly comment, which probably we'll also discuss next chapter, is the so-called theta term. Okay, so we know that E dot B is not a regular scalar; it's a pseudoscalar, right? So can we get a regular scalar out of E dot B? Okay. It turns out, yes, we could get a regular scalar out of E dot B. The only thing we need to do is to multiply another pseudoscalar, theta, with this whole thing. Okay. So this theta is a pseudoscalar. It's another pseudoscalar. Okay. And under space invariant or time reversal, E dot B changes sign, theta also changes sign. So the whole thing will not change sign. So we use a pseudoscalar times E dot B. That is a regular scalar. Okay. Because this pseudoscalar theta is a pseudoscalar. This pseudoscalar, the corresponding particle of this pseudoscalar, breaks the space invariant and the time reversal symmetry. Okay, so in particle physics, this theta field corresponds to a particle which is called axion. Okay, so this axion, this particle actually has a very important property. It breaks the space invariant and breaks the time reversal symmetry. Okay. So this particle is not part of a standard model, but it is one of the candidates for dark matter. Okay, and in condensed matter physics, this theta field, this object theta, measures how strong the system breaks the time reversal and the space invariant symmetry in my material, and it gives the so-called magnetoelectric field, magnetoelectric effect. Okay. So magnetoelectric effect means in this material, in some material, if it has magnetoelectric effect, it means that if I apply an electric field, it will generate magnetization. If I apply magnetic field, it will generate electric dipole. Okay, so that's opposite with what we learned in E and M1. In E and M1, we know if we want electric dipole moment, if we want to generate electric dipole moment, we can apply an electric field. Electric field gives me dipole moment, electric dipole moment. Magnetic field gives me a magnetic dipole moment. A magnetoelectric effect is a mixture, is a mixing, is swapping these two. Okay, you use E field to induce magnetic moment. You use magnetic field to induce electric dipole moment. That's called the magnetoelectric effect. And the magnetoelectric effect is induced by this theta term. And the strength of that effect is measured in the coefficient of this theta term. Okay, so nevertheless, so this this is one way to compensate and make the whole object a scalar. Okay, so to get a regular scalar, we need a pseudo scalar to multiply with it. Okay, we will probably come back to briefly discuss this in the next chapter when we discuss about the Lagrangian formalism. Okay, so that's all about E and B field. So so here let me summarize briefly. Okay, so in the last couple lectures, we learned we follow the important principle. Okay, the principle we follow is that we assume all different reference frames gives us the same physics law. The physics law stays the same in all different reference frames. That is a fundamental assumption called the principle of relativity, or the principle of special relativity. Okay, and following that principle, we showed that mathematically, this principle is equivalent to saying all our physics laws need to take the form of scalar equals scalar, vector equals vector, tensor equals tensor, etc. Okay. And in the last couple lectures, we followed this principle, and we looked at things related to E and M's. Okay, so we look at the charge density, current density. We look at the vector potential, scalar potential. We look at the E and the B field, and we look at all the physics principles that this object should obey, and we find that they all satisfy this relation. Okay, so they all satisfy this relation. And the next part, we will go a little bit further. Okay, so in the previous part, we are basically checking all the E and M field and all the Maxwell's equations follow this principle. So in the next part, we'll go to look at the equations of motions. Okay, and here we will assume equation of motion also follow the same principle, so that the equation of motion is also invariant from one reference frame when we go from one reference frame to another reference frame. Okay, and then we will utilize this scalar equals scalar, vector equals vector, and tensor equals tensor structure as a constraint for our equation of motion. Okay, and in this part, we will utilize this as a constraint for our equation of motion and require our equation of motion follow this structure. And there we will see what are the consequences. Okay, so the story in the next part will be a little bit different from what we learned before, what we learned in the previous sections. In the previous sections, we didn't modify any physics law we learned. So for example, Maxwell's equation, we have the same Maxwell's equation. We just reorganize Maxwell's equation in the structure of vector equals vector, tensor equals tensor. Okay, and in this part, in 3.2, when we try to do the same thing for equation of motion, we will notice that we can't do this for the regular equation of motion Newton told us. We have to modify the equation of motion Newton gives us in order to obey this scalar equals scalar, vector equals vector, tensor equals tensor structure. Okay, so in this section, we will start to modify physics laws, not just take the existing physics laws as granted. We need to modify them to make them obey this principle. Okay, and of course, when we modify what Newton told us, we need to keep in mind one other important constraint, which we discussed earlier in this semester. The other constraint is Newton's law cannot be wrong if the motion velocity is much smaller than speed of light. Okay, because Newton's law has been studied and tested in numerous experiments. Okay, including motion of the planets, motion of the stars, rockets, and the motion of all our mechanics we have in our daily life. Okay, and in all these experiments, it has showed us as long as the velocity of our object is small compared with speed of light, Newton's law is gives very accurate prediction. So which means if we want to modify our theory, we can't modify it too dramatically. we need to make sure when velocity is small, when things are moving slowly, much slower than the speed of light, everything goes back to Newton's structure. Okay. In other words, in this chapter, in this section, we will have two constraints when we rewrite our equation of motion, when we modify our physics laws. First requirement is we need to make sure that our theory satisfies the scalar equals scalar, vector equals vector, tensor equals tensor structure. Okay, that is the only way to guarantee all physics laws stay the same in different reference frame. Okay, that's one constraint. The second constraint is when we modify this, we need to make sure that our modification, our new physics law, recovers Newton's law when the velocity of my particle is low. Okay, so that's what we are going to do. Okay, so let's look at the equation of motion. So equation of motion actually contains two parts. Okay, one is the motion part, and the other part is the cause of the motion. Okay, so cause of the motion and motion. That relation is called the equation of motion. Okay, the cause of motion, of course, is what we call the force, and motion itself should be described by, say, velocity. Okay, so let's first look at the velocity side, and then we will look at the cause of the motion side. So for the velocity side, for the motion side, we need to define first velocity. And the velocity, we all know how to define that. So in a 3D space, the velocity is dx dt, dy dt, dz dt. This is velocity along x, velocity along y, velocity along z axis. Okay. And of course, we can take another derivative and define accelerations, and which is also a 3D scalar. Okay. But but here we can't do that. Okay. The reason we can't do this is because this guy, dx dt, dy dt, dz dt, is not a structure of 4D scalar, 4D vector, 4D tensor. Okay, this dx dt, dy dt, dz dt is neither a 4D scalar, nor a 4D vector, nor a 4D tensor. Okay, if we want to write down our equation of motion, we have to follow the structure of scalar equals scalar, vector equals vector, tensor equals tensor, so we can't use them. Okay, this guy is neither of them, so we can't do it. So what should we do? Well, the most important thing is we need to replace what Newton used, for example, the Newton's velocity and Newton's acceleration, with something else. And that something else is very similar to what Newton utilized, but it allows us to organize things into this scalar, vector, 4D scalar, 4D vector, 4D tensor structure. Okay, we need to organize it into this structure. But at the same time, we cannot be too much different from Newton, because we know when velocity is small, we need to recover Newton. Okay, and what can we do? Well, there are two problems we need to overcome here. Okay, so this guy is not a 4D scalar, 4D vector, 4D tensor for two reasons. The first reason, the numerator x, y, z are not a 4D scalar. Of x, y, z themselves is a 3D vector. It's not a 4D vector. Okay, x, y, z themselves is only a 3D vector. And the second problem of this is dt. dt, this derivative, is not a scalar, not a 4D scalar, and not a 4D vector either. This t itself. Okay, so let's first fix the numerator. Okay. The numerator x, y, z is not a 4D vector. We know x, y, z is not 4D vector, but we do know if we just add one more component to it, c times t, then this whole thing becomes a 4D vector. Okay, which means for the numerator x, y, z, we should modify that. We should not use x, y, z anymore. We should instead use x, y, z and ct. Okay, so this is a 4D vector. So the numerator is a 4D vector, very nice. But the denominator, we still have a problem. Denominator is time. Time is neither a 4D vector or a 4D scalar. Okay, time is one component of a 4D vector. It's only part of 4D vector. It itself is not a vector or a scalar. Okay. So we need to replace this derivative of time to another derivative, which is very similar to derivative of time, but it follows the scalar, vector, or tensor structure. And what is some object really, really close to time, but also at the same time it's a scalar or vector or tensor? Well, the simplest option is the proper time. Okay. The proper time is a 3D scalar, as we mentioned earlier. Okay. The proper time is the time that's associated to a moving object itself. Okay. So for any moving object, The proper time is time measured by the moving object itself. That proper time is an intrinsic property of a moving object. It doesn't matter which reference frame we are looking at. Whatever reference frame will give you different lab time, but the proper time will always be the same. So proper time is a scalar. Okay. Proper time is very similar to time. They only differ by a factor gamma. This gamma is a Lorentz boost factor. Okay, it's very similar to time, but it becomes a scalar. Okay. So if we replace time with proper time, this proper time derivative, then this whole thing becomes a scalar. Proper time is scalar times a vector. And the scalar times a vector we know is a vector. So this is a 4-dimensional vector. And this 4-dimensional vector is very similar to the velocity we defined earlier on. Sorry, velocity we defined in Newton's mechanics. But it is a really 4D scalar. Sorry, 4D vector. Sorry for that. Okay, and this is the velocity we should use in special relativity. This is a so-called 4D velocity, and it's usually labeled using U instead of V to distinguish 4D velocity and 3D velocity. Okay, so the 4D velocity is a 4D vector. It has 4 components, and it's actually the proper time derivative of Ct, x, y, and z. Okay, and if we write down the derivative, into each component, this is what we have. The first component is speed of light, dt d tau. T is lab time, tau is the proper time. And the xyz component is dx d tau, dy d tau, dz d tau. Okay, and we can rewrite this dx d tau, dy d tau, dz d tau as using the chain rule, dx dt, dt d tau, dy dt, dt d tau, dz dt, oops, sorry, dz dt, dt d tau. Okay, and the chain rule actually, this is just the chain rule, nothing fancy. Okay, if you cancel this 2 dt, you go back to the dz d tau. Okay, so we can rewrite these last 3 terms like this. Okay, and what is dt d tau? Notice that there is a dt d tau factor in every single term. Okay, dt d tau, dt d tau, dt d tau, dt d tau. I can put this common factor out, and this common factor dt d tau, the ratio between lab time and proper time is just gamma. Okay, the same gamma factor we defined earlier. 1 over square root 1 minus v square over c square. It's just gamma. Okay, so the 4D velocity is actually speed of light and the 3D velocity multiplied by gamma. That's our 4D velocity. And this 4D velocity is very close to 3D velocity. And most importantly, when velocity is small, when v is small, gamma becomes 1. Okay, and if gamma is 1, then the 1, 2, 3 component of this 4D vector recover exactly the velocity Newton defined, vx, vy, vz. Okay. Last 3 component of the 4D velocity and the conventional 4D velocity we defined in Newton's mechanics, the conventional 3D velocity we defined in Newton's mechanics are pretty much the same thing. They only differ by a factor of gamma, and this gamma becomes 0. Sorry, this gamma becomes 1 when the velocity is small. Okay, so this is the 4D velocity. So once we define the 4D velocity, we can immediately define the so-called 4D momentum. Okay, and 4D momentum is actually again a 4-dimensional vector. Okay, and the 4D velocity is a 4D vector. We want momentum to be also a vector, which means we need to multiply this velocity vector with a scalar. Scalar multiplied by a vector is a vector. Okay, so we need to multiply this 4D velocity with a scalar to get 4D momentum vector. And this scalar should be very close to mass. Okay, because in low velocity, we want to recover Newton. Newton tells us it's mass, so this must be something very closely related with mass, but it needs to be a 4D scalar. So what is a 4D scalar that is very much closely related to mass? Of course, the obvious candidate is the rest mass of an object. Okay, as we know, the mass of particle changes if we go from one reference frame to another, because mass depends on velocity in special relativity. But the rest mass doesn't. Rest mass of object is an intrinsic property. If we just do a Lorentz boost, it will not change the rest mass. Okay, so rest mass is scalar. That scalar times the 4D velocity gives me a 4D vector. This 4D vector is a 4D momentum vector. Okay, so this is a 4D momentum vector, and it's just the gamma, the same gamma factor we defined earlier, Lorentz boost times the mass. Sorry, this m0 is the rest mass of my object, and the 4 components speed of light, velocity along x, velocity along y, velocity along z. Okay, so that's the 4D momentum. Okay, so now we know how to define momentum, how to define velocity in the 4D structure. Okay, now let's look at the cause of motion. Okay, the cause of motion is, of course, force. Okay, and for E and M, sometimes we need to discuss force. Sometimes we need to discuss the so-called force density. So in this section, we'll look at these 2 quantities together: force and force density. Okay, so force, of course, is very important. Okay, it's a cause of motion. For example, we know dp dt, the momentum, time derivative of momentum should be force. That's what Newton told us. Okay, and we also know the energy derivative to time, which is energy is actually the energy derivative to time is the same as the derivative of work to time. This W is the work done by the exterior, the environment to the system. Okay, and the work derivative of time is the so-called power. Okay, so Newton also told us power should equal to force times the velocity of the object. Okay, a small notation here, a small note here. This P is power. Okay, they should not be confused with this P. This P is momentum. Unfortunately, in physics, we use the same letter for different quantities, like momentum and power. They all share letter P and also pressure. So here I want to highlight that this P and this P are different. Okay, so force, of course, is a very important thing in any equation of motion. Okay? In the equation of motion. Okay. Now let's look at force in E and M. Okay, the force in E and M we know is this. More precisely, the force density in E and M is this. The first term is an electric force. It's electric field times the charge density. That's the force comes from charged particles or charged objects in an electric field. Okay, so on this side we have force density. That's force per volume. On this side we have charge density. That's charge per volume. Okay, and that's from electric field. And the magnetic field also gives us a force. This is so-called Lorentz force. Lorentz force is a cross product between charge current density, J, current density, cross product with magnetic field strength B. Okay, so from force from electric field and Lorentz field add up together is my total force density. If we want to write down the XYZ component, this is what the XYZ component looks like, and we have already learned this in E and M1. Okay, and this is, again, I want to emphasize, this is force density, force per volume. It's not the force itself, the force on object. If you want to know the total force on object, what we need to do is a 3D integral. Okay, force density and point R integrated over R and integrated over the whole size of my object. Okay, and this is the force we utilize in E and M. Okay, but again, in order to write down equation of motion, we need to modify this force. And the problem of this force is, again, this force is not a 4D scalar tensor or vector. Okay, we need to reorganize the force, write down something really, really similar to force, but this new object need to take the structure of scalar, either a scalar or vector or tensor. Okay, and at the same time, this new object need to be very similar to the Newton's definition of force. Okay, so that we can recover Newton's law. Okay, now what should we do? Well, the way to get the proper force description, force vector, is to look at this equation. Okay, so this equation, we know that the definition of force involves 2 objects. One is rho and j. Okay, we know rho and j combined together form a 4D vector. That's our charge density, current density 4D vector. That's one object. Okay. The second object we need to define force here, force density here, is E and B. E and B is a rank 2 tensor. It's F tensor we defined earlier. Okay. So in other words, force density is actually my F tensor multiplied with the vector of rho and j. Okay, rho and j gives me a vector, f gives me a tensor. I multiply them together, somehow I get this force. Okay, and what multiplication should I use here? Which multiplication should I use here? Well, it turns out this is a inner product. Okay, so here let me briefly discuss about the inner product between a tensor and a vector. Okay, so the inner product between a tensor and a vector is this. So say M is a tensor, X is a vector, then their inner product is M times the metric tensor times the vector. Okay, M is a tensor, so it's a 4x4 matrix. G is a tensor, 4x4 matrix, metric tensor. Okay, and X is a 4D vector, it's a column vector. Matrix times column vector gives me a column vector. Okay, and so this is actually the so-called inner product between a tensor and a vector. And the inner product between a tensor and a vector gives me a vector. Okay, so here let me first prove to you, prove to you, a tensor times metric tensor times a vector, this is so-called inner product, gives me a vector. So this whole thing is a vector. In order to prove this is a vector, we do the same. We do a Lorentz boost, or 4D rotation. Okay, under Lorentz boost, this M tensor, M is a tensor, so the tensor should become this. For a tensor under Lorentz boost, I multiply one transformation on one side, another transformation matrix with a transpose on the other side. Okay, and the G doesn't change. Metric tensor doesn't change under Lorentz boost. And for X, X is a vector. So X, the vector change, transformation of a vector is a matrix times a vector. Okay, that's a Lorentz boost of a vector. And with this structure, we have a bunch of R and M and G and X times together. Let's regroup these three objects together. Let's regroup RT, G, R together, these three things together. RT, G, R is the Lorentz boost of metric tensor G. And we know by definition, Lorentz boost do not change metric tensor. So RTGR is G. Okay, if we replace RTGR with G, this whole thing we have MGX here. Okay, and if we group MGX together, we showed that under Lorentz boost, this whole thing becomes this. Okay, this means MGX is a vector, because for a vector under Lorentz boost, vector changes like this. Under Lorentz boost, a vector transforms as R times this object. That's the definition of 4D vector. So any object in 4 dimension, if we do a Lorentz boost or 3D or 4D rotation, it transforms the same as coordinate. It's a 4D vector. So this is 4D vector. So the bottom line, any rank 2 tensor in 4D and any vector in 4D, we can multiply them together in this way. This is called their inner product. And this inner product gives me a vector. Okay. So here, let me look at the inner product of F. By the way, this F is not force. Sorry again for using the same letter for different things. Unfortunately, that's what we do in physics. Sometimes we don't have enough letters. This F is a rank 2 tensor of E and B field. Okay, and we have a 4D vector J. This 4D vector J is the charge density, current density vector we learned earlier. Okay, so we have rank 2 tensor F, which is E and B field, and we have a 4D vector, which is charge density and current density, and we can calculate their inner product. Okay, that's exactly the same structure I was telling here. A tensor, metric tensor, vector. Tensor, metric tensor, vector. So this inner product should give us a vector. Let's look at that vector, what that vector is. Okay, F, we know F, it's E and B. We know G, metric tensor, 1, minus 1, minus 1, minus 1. That's our metric tensor. And we know the charge density, current density 4D vector. That's speed of light, charge density, and current density. Okay. Matrix times column vector. We just do the standard multiplication of matrices and vectors. Here I multiply the G and this column vector together. G and column vector multiplied together is this column vector. And then I multiply this matrix with this column vector. I got this column vector. Okay. And if we massage this column vector together a little bit, so let's just look at the last 3 components first. These last 3 components are precisely force density along X, force density along Y, force density along Z. If we remember, force density is this, and compare this result with what we have here, this last 3 components Fx, Fy, and Fz. The first component is a little bit different. The first component has a 1 over c, speed of light, okay? And it's an inner product, it's a dot product, it's a dot product between E and J. This is E is a 3D vector, electric field, J is a 3D vector, 3D current density, and their dot product gives me a 3D scalar divided by C. That gives me the first component, okay? So from this construction, we learned that force density, Fx, Fy, Fz, force density, Fx, Fy, and Fz, is actually part of a 4D vector. Okay? This 4D vector is constructed from a E and B field tensor, inner product with charge density, current density vector. Okay? The first component is E dot J over C. The last three components of this 4D vector is Fx, Fy, and Fz, force density along X, Y, and Z direction. Okay. And this is actually very important conclusion. It means in the future, if we want to write down the equation of motion, and we want to organize equation of motion into this 4D scalar vector tensor structure, we need to replace force by this 4D vector. Okay, so before we conclude today's lecture, I want to mention one more thing, actually a couple more things, two more things. The first thing I want to mention, I want to talk about is this first component. Okay, this first component in my 4D force vector. Okay, this four component is E dot J. What is E dot J? Well, it turns out E dot J is related with power. I'll say power density. Okay. So we know power, okay? Actually, I mentioned the power slightly earlier on. Okay? Power is derivative of work to time. It's a work done by the exterior environment to my system per time, derivative of work per time. Okay, so that's what we call power in Newton's mechanics. Newton's mechanics told us P is force dot velocity. So P here is charge Q, electric field dot velocity. Okay, and this is power. This is power on an object. And if we look at the power per volume, or the so-called power density, power in each unit volume, and the power per volume is actually the same formula, except we change charge Q with charge density, charge per volume. Okay. If we want power per volume, E and V remains the same. We just replace Q with charge density. Okay, so that this is a power per volume. And unfortunately, power per volume is often also called W, and that is the same letter we use for work. Unfortunately, in physics, we always run out of letters. So, but this W should not be confused with work. It's power density, power per volume. Okay, and this power per volume, if we look at this, we have charge density times velocity. And what is charge density times velocity? Charge density times velocity is actually the definition of current density. Okay, so this power per volume, power density, is actually E dot J, E dot J. Okay, so this first component, the E dot J, is actually measuring power per volume. It's a power density divided by speed of light. Okay, so in special relativity, when we organize everything into 4D scalars vectors, force is part of 4D vector. And the other component, in addition to the three directional force, we need another component to make a 4D vector. That additional component is power per volume, also called power density. Okay. Power density and the three components of force gives me a 4D vector. That's my four-dimensional force. Okay, so that's a four-dimensional force density. So power density, force density gives me a 4D vector. That's a 4D force density vector. So the last topic I want to mention is force. Okay, we are always talking about force density here. Force per volume, power per volume, etc. It's density. It's not force itself yet. In order to go from force density to force, we need to do a spatial interval. Okay, this is force per volume. We calculate we integrate over all the volume, so we get the total force. But this formula also needs modification. Okay, Because eventually we want a force, which is a 4D vector. If we want the force to be a 4D vector, force density we already know is already a 4D vector. This integral cannot give me a 4D force. Force density is a 4D vector. The problem is this spatial integral. dx, dy, dz is not a 4D scalar. Okay? Volume is not invariant under Lorentz boost. This is because of length contraction. Okay? If we change reference frame, the length along the x direction, along the velocity direction will change, contract. And that length contraction means this volume is changing. If the volume is changing, this volume is not a scalar. If it's not a scalar, something not a scalar times a vector would not give you a vector. Okay, so this definition of force needs modification. And the goal of this modification is to define a new force, which is indeed a vector. In other words, we need to modify the volume into something which is a scalar. And the scalar volume is actually very easy to define. Its original definition of volume, dx, dy, dz, multiplied by gamma. Okay, this gamma is the same gamma we use in the Lorentz boost. Okay, it's 1 over square root of 1 minus velocity squared over c squared. Okay. The reason this gamma helped us is because under Lorentz boost, say we go to a different reference frame with velocity along x. Okay, under Lorentz boost, this x changes with factor gamma. That precisely cancels this gamma. Okay? So this whole thing, dx, dy, dz, and gamma, gives me a scalar volume. And that volume is independent of reference frames. And by the way, this scalar volume is pretty much the same thing as proper time. It's a space version of the proper time. This is the volume of the object measured in the reference frame where this object is not moving. Okay, so this is a volume measured in the reference frame where this particle is not moving. If we have a moving object, we need to choose a reference frame where this moving object is not moving. This is the rest volume. Okay, so proper time is the time measured in the rest frame, and this volume is a volume measured in the rest frame. So same as proper time, this guy is also a scalar. Okay, so because this guy is a scalar, now the scalar times the vector is a vector. So this integral gives me a proper definition of a 4D vector. That is a 4D force vector we are going to utilize when we write down the equation of motion. Okay, and that's the force. Okay, let's explicitly write down this this formula here. Okay, so this is, let me put this gamma factor out, dx, dy, dz. The first component we already know it's power density divided by speed of light. The last three components are the force density. Okay? And when we do the integral of space, when we do the space integral, power density after space integral becomes power. Okay, that's the definition. Power density integral over space becomes power. And the force density over integrated over space becomes force. So this power and the force are the definition of what Newton used. This is Newton's power, Newton's force. Okay, and Newton's power and the Newton's force, if we multiply them with a gamma factor, it gives us the 4D force vector, the 4D vector of force. Okay, so the bottom line, when we do equation of motion, whenever we need force, we should replace the conventional definition of force with this 4D vector of force. And this 4D vector of force will allow us to write down equation of motion in the structure of scalar equals scalar, vector equals vector, and tensor equals tensor. Okay, I think this is a good point to stop. So in today's lecture, we did two things. One is we finished our discussion about the E and B field. And most importantly, we showed that the E and B field, we can make two scalars out of the E and B field. And you will do some fun homework problems to practice and to utilize that, to prove that congruent and utilize that congruent to prove a couple of things. And in the second part of today's lecture, we start to describe the equation, start to construct the equation of motion and try to organize the equation of motion in this scalar equals scalar, vector equals vector structure. And to do that, it turns out we first define the velocity, what is a proper velocity in 4D space, and what is the force and the force density in 4D space. Okay. And then in the next lecture, we will use the velocity and the momentum we defined today and the force we defined today to write down equation of motion in this scalar equals scalar, vector equals vector structure, and see what are their consequences. Okay, I think this is a good point to stop, and I will see you next time.